Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll start learning about the processes of radioactive decay, also referred to as radioactivity, among unstable nuclei. Now there are three main processes by which unstable nuclei emit particles to go on to become a stable nuclei. The first is called alpha decay. The second is beta decay, which is itself divided into two parts, beta plus decay and beta minus decay. And then the third one, which is gamma decay, referred to as alpha, beta and gamma. So let's start off with the first one, alpha decay. We already know what an alpha particle is. An alpha particle is basically the nucleus of helium, that is 4He2, without the electrons. So many times a heavy nuclei will emit an alpha particle and become a somewhat lighter nuclei, and we know that as you go into the heavy range, heavier nuclei are more unstable than lighter nuclei. So when it becomes a lighter nuclei, it will become more stable. The general equation of this would be AXZ, which is the symbol for a generic element, becomes, first of all, it emits 4He2, the nucleus, and then it becomes Y. Now we can easily match the mass number and atomic number to get these values. If this is Z and this is 2, this should look more like 2, I apologize. Then this is Z minus 2 and this is A minus 4. So it emits a 4,2 helium nucleus, also called an alpha particle, and this is called the parent nucleus, and this Y is called the daughter nucleus. Now alpha decay occurs in all elements, or rather we should say all nuclei, that's the better word, with A greater than 210. So very heavy nuclei will almost always emit an alpha particle and in turn become a somewhat lighter nuclei. Now obviously, if this is supposed to be a reaction which makes this nuclei more stable, then the combined rest mass energies of these two has to be smaller than this rest mass energy. Because if the rest mass energy is smaller, that means the final energy is smaller than the initial energy. That means the particle has become more stable. And the difference in these rest mass energies, and this goes not only for alpha decay but for any nuclear reaction, the difference in rest mass energies is called the Q value of a reaction. And it is basically equal to the initial energy minus the final energy. If Q is greater than 0, that means the reaction will take place. And if Q is less than 0, that means the final products have a higher energy than the initial products. So you'll need to give energy to the initial products to make the final products, as opposed to the initial energy, initial products spontaneously converting to the final and releasing some energy. Now that does not mean Q less than 0 reactions do not take place. They do, but they have to be aided or catalyzed by some way. Naturally left unaided spontaneously, Q less than 0 reactions will not take place. Let's look at the reaction again we were talking about. AXZ becomes A minus 4 Y Z minus 2 plus 4He2. What is the initial energy? That will be the mass of AXZ times C squared. What is the final energy? That is the mass of A minus 4 Y Z minus 2 plus the mass of 4He2 whole times C square. So what is the Q value of this reaction? That is mass of AXZ minus mass of A minus 4 Y Z minus 2 minus the mass of 4 He2 times C square. Never forget the C square. That is the conversion factor from mass to energy. And we already know that the combined rest mass energies of the final products has to be smaller than the rest mass energy of the initial product. Otherwise, the reaction will not take place. The reaction takes place because Y is more stable than X. That is only possible if this whole system has a smaller rest mass energy than this system. Now, like I said, unless otherwise mentioned, we'll assume that the atomic masses are taken, including the masses of the nucleus, but except in very special cases, it won't matter. So this is the atomic mass, including the mass of the electrons. So this is the atomic masses, including the mass of the electrons. What would happen if we were not to take the mass of the electrons? Then Q would be the nuclear mass, let's call this M dash for now, nuclear mass of AXZ minus nuclear mass of A minus 4 YZ minus 2 minus nuclear mass of 4 He2 whole multiplied by C squared. But then what do we need to do to get the nuclear mass from here? We just have to subtract from this minus Z times the mass of an electron. We have to subtract from this minus Z minus 2 times the mass of an electron from this thing. And from this, we have to subtract minus 2 times the mass of an electron. And you can see that all the masses of the electrons, they'll end up cancelling out. So this is another one of those regular cases where it doesn't matter in the formula whether you use atomic mass or nuclear mass, the formulas still have the exact same structure. Also, the energy released, this Q value is the final energy released, and that is released generally as the kinetic energy of the product particles. Now, since generally this takes place when A is greater than 210, that means even A minus 4 will be much greater than 4. So the mass of the daughter nucleus is much larger than the mass of the alpha particle, and we assume that because the daughter nucleus is so heavy, it does not move appreciably, and all the kinetic energy is given to the alpha particle. So the kinetic energy of the alpha particle in an alpha decay is basically the Q value of the reaction, and it is the same in every decay scheme, right? If A is going to Y and releasing alpha particle, then if it happens 10 million times, then all 10 million alpha particles will have approximately the same energy, because we've neglected the kinetic energy of this nucleus because it is much larger compared to this nucleus. Let's look at some properties of alpha rays. What are alpha rays? They are just a stream of alpha particles coming from a bulk material. So if you have a bulk material of parent nucleus, it converts to daughter nucleus, it will release a stream of alpha particles. And let's look at some of the properties of these alpha rays. The first is they can be deflected by electromagnetic fields. As alpha particles are positively charged. So not only will they be deflected, but they will be deflected in the same direction as positively charged particles would be deflected. Secondly, they have low penetrating power . And even in air, their intensity falls to a very low value within centimeters. Third, if you look at the Q value and use it to be half mv square for the kinetic energy, then the speed of alpha particles coming from radioactive decay is very large, approximately 10 to the power 8 meters per second. And this is where we see why nuclear energy is so important. A very small change in mass because of that C square factor can give us a very large amount of energy. Right. Also, finally, all alpha particles coming from a decay scheme have approximately same kinetic energy. because the daughter nucleus does not share an appreciable amount of kinetic energy. Right? So this is alpha decay. Let's move on to the next one, which is beta decay. It has two variations, beta minus decay and beta plus decay. Beta minus decay happens when a neutron converts to a proton, and beta plus decay happens when a proton converts to a neutron. Now, why do these particles convert to another particle? That is because of the presence of a weak nuclear force. We have seen very early on in our video that there are four fundamental forces in nature: the gravitational force, the electromagnetic force, the strong nuclear force, and we see the fourth one now, the weak nuclear force. The strong nuclear force has a very small nuclear range of the order of 1 femtometer, but the weak nuclear force has a range even smaller than that. The weak nuclear force has such a small range that it only acts within a nucleon. That means the nuclear range of the weak nuclear force is actually of the order of a radius of a proton or neutron, as opposed to the strong nuclear force, which has a nuclear range of the order of the radius of the nucleus. So because it only acts within a nucleon, you only see its effects when one nucleon converts to another nucleon. Right. So first let's look at beta minus decay, in which a neutron converts to a proton. Now, we can see right now actually that this has a Q value greater than 0 and this has a Q value less than 0, because we know the mass of the neutron is greater than the mass of the proton. That's why beta minus decay happen readily in nature, but you have to in some way catalyze the beta plus decay. It does not generally happen spontaneously in nature, though because it can be made to happen, it is our job to study it. So beta minus decay, the general reaction for that is a neutron converts to a proton plus an electron, and if you see, the mass of the proton plus the mass of the electron is still combined smaller than the mass of the neutron. And this also takes care of charge conservation, because this is electrically neutral and proton has a positive charge and electron has an equally opposite negative charge. But there's also another particle, a fundamental particle, which is emitted, and this is probably something new to you. It is called an antineutrino. We'll see that every particle has its antiparticle. Electrons have their antiparticles called positrons, and antineutrinos have an antiparticle neutrinos, and both of those actually occur in beta plus decay. So I'll just write that down now, we'll study it in a moment. Beta plus decay is proton goes to neutron plus a positron plus mu, which is a neutrino, and this is a positron. We'll discuss these both in a moment. Let's just look at the beta minus decay for now. So beta minus decay says a neutron is converted to a proton plus an electron plus an antineutrino. Another way of writing this in terms of nuclei would be AXZ goes to, now neutron converts to proton, so A remains the same, Z increases by 1. So it becomes AYZ plus 1 plus an electron plus a mu, or sometimes it is also written as AYZ plus 1 plus a beta minus plus mu. This bar denotes the antiparticle of a neutrino, the antineutrino. So let's look at the antineutrino first. It has a property, and the property of the neutrinos and the antineutrinos are the same, so I'll not repeat it for the neutrino. These antineutrinos and neutrinos are chargeless, massless, so they're like photons. Chargeless, massless, they have zero mass, though they can have kinetic energy just like photons can have energy, though they don't have any mass, and they have a spin quantum number plus minus half, just like electrons. So this is the property of antineutrinos and also the property of neutrinos. Now let's look at the Q value of this reaction. So what is the initial energy? The initial energy is the mass of AXZ times C squared. The final energy is the mass of A y z plus 1 plus the mass of an electron times c square, which means Q is the mass of AXZ minus the mass of AYZ plus 1 minus the mass of an electron times c square. Now here we've used atomic masses, right? But would the formula be still the same if we were to use nuclear masses? No. And this is the one exception where you do not get the same result, and obviously if you do not get the same result, then the nuclear masses are to be used, right? So in this case, this is the, if we assume this to be the mass of the nucleus, let's take this m dash and mass of the electron, this would give us the correct result. Remember, nuclear masses are to be used generally because we have a nuclear reaction. But my hypothesis was that atomic masses will generally give the exact same formula because the mass of the electrons will cancel out, except in specific cases. And this is that specific case. This is the only case in which the formula by using nuclear masses and atomic masses is different, and obviously then you have to use the nuclear masses. So if m of AXZ corresponds to the mass of the nucleus without adding the mass of the Z electrons, then this formula is true. What would be different if we were to use the atomic masses? Well, what would happen in that case would be, you would have U initial is equal to mass of AXZ minus Z times mass of an electron. This is the nuclear mass and this is the atomic mass. U final is equal to mass of AYZ plus 1 minus Z plus 1 times the mass of an electron minus the mass of an electron. And if you take Ui minus Uf, you'll actually see that the electrons do not cancel out. This should be plus, sorry. In this case they do, but in this case they don't. Z minus, this is minus Z minus 1 plus 1 is minus Z, and minus Z will cancel out. So you will have just this minus this. So just to recap, to repeat it further, if you use nuclear masses, then the formula is m times AXZ minus m times AYZ plus 1 minus ME times C square. The equation again is AXZ goes to AYZ plus 1 plus electron plus neutrino, which doesn't have any mass, antineutrino. Now, you might be wondering why use atomic masses at all. The nuclear masses always give the direct result. The mass of this nucleus, the mass of this nucleus, the mass of this nucleus, just add up all the masses of the nuclei and subtract the final from the initial. However, we already have a list of atomic masses available, and so it makes sense to try to reorder it in terms of atomic masses. However, if atomic masses are used, then we saw the electrons were cancelling, and in this case it was mass of AXZ minus mass of AYZ plus 1 C square. Because the reason for that is an extra electron is being created, so the mass of the electrons will not cancel out. By and large, you will be given the atomic masses, so this is the formula you need to use, and this is where students get a little bit confused. I generally always try to use the nuclear masses because they are more natural. I mean, this is the reaction which is occurring between nucleons, right? Between nuclei. There are no Z electrons in this one. Electrons are not taking part. So you take the mass of this entity, which would be the nuclear mass of AXZ, take the mass of this entity, take the mass of this entity. That's more natural. However, we do not readily have a data of nuclear masses available. We do have a data of atomic masses available, and in terms of atomic masses, you just subtract minus ZME from the atomic mass to get the nuclear mass, minus Z plus 1 and minus this, and you'll see that the mass of the electron will cancel out, and this will be the result. So this is the one you have to remember. In every case, now we'll do beta plus decay, and even in that, nuclear masses and atomic masses give the same formula. So specifically for the case of beta minus decay, this is the formula for atomic mass, this is the formula for nuclear mass. In all others, they're the same formula. I would really hope you don't try to remember this stuff, but try to solve it yourself and figure it out, because that's when you will really understand it. Right. The other important thing here is that if we assume this to be stationary, then all the kinetic energy is not given to the electron. Some kinetic energy is also taken by the antineutrino. So though the kinetic energy of the alpha particle is equal to the Q value of the alpha decay, the kinetic energy of the electron is between 0 and Q. It does not have to be 0, it does not have to be Q. The kinetic energy of the electron depends on how much kinetic energy is shared by the antineutrino. Right. Let's look at beta plus decay now. Beta plus decay means proton converts to a neutron plus a positron plus a neutrino. Neutrino, like an antineutrino, is a chargeless, massless particle which has a spin quantum number of plus minus half, and a positron is basically exactly the same as an electron in charge and its in mass, and the charge has the same magnitude as that of an electron but a positive sign. So you can think of it as the charge of a proton but the mass of an electron. And even here the charge is conserved because this has 1 unit positive charge and this combined system has 1 unit positive charge. Now here again we'll see that the equations are same whether we use atomic or nuclear masses. Using the nuclei, the equation would be AXZ becomes AYZ minus 1 because the proton is converted to a neutron plus a positron or a beta plus particle plus a neutrino. Right. Now let's say we were to use nuclear masses. That we'll denote by m dash. Then the Q value would be m dash of AXZ minus m dash of AYZ minus 1 minus m dash of an electron, or m of an electron. They're the same. But if we were to use atomic masses, then on the LHS we would have mass of AXZ minus Z times mass of an electron. On the other side we would have mass of m dash is the nuclear mass, m is the atomic mass, remember. AYZ minus 1 minus Z minus 1 times the mass of an electron plus the mass of an electron. And you can see that this and this and this cancel. So whether or not you use nuclear or atomic masses, sorry, it doesn't cancel out. This is plus and plus. So in the end we'll have 2 Me left. And even in this case, whether you use atomic or nuclear masses gives different results. This is using nuclear masses. Using atomic masses, it would be m of AXZ minus m of AYZ minus 1 minus 2 times the mass of an electron. So remember, whenever new electrons are created, the mass of the electrons will not cancel out, and there are different formulas by using atomic and nuclear masses. This is atomic. But for alpha decays and for general processes in which no electrons are created, it doesn't matter whether you use nuclear masses or electronic masses. Let's look at some properties of beta rays. We don't need to go in detail because we've already seen properties of cathode rays, and a stream of electrons is called beta rays if they are emitted from radioactive materials. But whether it's beta rays, cathode rays, thermions, photoelectrons, they all have the exact same property. The only difference is the origin, how they are formed. Beta particles are formed in nuclear transformations. Also, they can be deflected by electric and magnetic field. I'll just write it down. Same as electrons, same as cathode rays, right? Because in a previous video we've seen the properties of cathode rays. And just like cathode rays can be deflected, by EM fields. And the most important property, not all beta particles have the same energy as opposed to alpha particles. Because some and the properties of beta plus particles are pretty much exactly same as beta minus particles. The only difference is they have a positive charge as opposed to a negative charge. Finally, let's look at the third and the simplest form of radiation, gamma rays. Now, whenever a parent nucleus emits some alpha or beta particles and becomes a daughter nucleus, often the daughter nucleus may be in an excited state. Now, just like electrons in an atom, nuclei have discrete quantum states with particular energies. And if the nucleus is at an excited state, and this is the ground state, then it can come down to a ground state by emitting a photon. Now we saw in Bohr's model that when electrons come from one state to another in a hydrogen atom, the energies, depending on whether it's the Lyman-Balmer or Paschen series, fall in the ultraviolet, visible or infrared rays. But the energy of nuclei is much higher than the energy of electrons bound to an atom, and therefore lambda is equal to hc by E is much smaller because E is much larger. So small in fact that the wavelengths are even smaller than X-rays, and we give them a new name which is called gamma rays. So generally a nucleus might emit an alpha particle and or a beta particle and become a daughter nucleus, and that daughter nucleus may or may not be in an excited state. If it's in an excited state, then it will emit a photon to come to its ground state, and because the energies of the nuclei are so high, this photon generally falls in the range of gamma rays. Now alpha, beta and gamma rays collectively are called radioactive decays, and the materials undergoing radioactive decays are called radioactive materials. Alpha, beta and gamma are called nuclear radiation, and let's look at the properties of gamma rays now. Most of the properties you already know because gamma rays are basically photons. They are electromagnetic radiation of very short wavelength. Unlike alpha and beta particle, they are massless particles because we already know photons do not have any mass. Also, they are chargeless because photons are chargeless. So they cannot be deflected by electric or magnetic fields, and all photons coming from a decay scheme have the same energy. Also, because they are electromagnetic waves, they travel in vacuum at the speed of light. Now we've seen the qualitative nature of radioactivity. In the next video, we start looking at the mathematics of radioactive decay. Thank you.